In this session, we are going to talk about indeterminate forms and L'Hopital's rule. L'Hopital's rule was named after the French mathematician L'Hopital. His full name was Guillaume François Otto Marquis de L'Hopital. Although the rule is attributed to L'Hopital, but the theorem was first introduced to him by Swiss mathematician John Bernoulli. So here we can see that there is a word indeterminate. So what does it mean? Indeterminate means something which is not exactly known. So we have seen that whenever we are trying to find the derivatives of any function, the notion of limits is useful. In fact, in the definition of derivative, the concept of limit is there. But now we will see how derivatives can be applied to evaluate the limits of any function. So that means in L'Hopital's rule, we have to apply the concept of derivatives. That means whatever formulas, rules we have learned for derivatives, all will be applicable if we want to apply L'Hopital's rule. So before L'Hopital's rule, we have to have a good control over derivatives. Since we are going to evaluate limits of any function using L'Hopital's rule, so let's recall a limit of the form limit of f of x over g of x when x approaches a. So suppose we have this limit. Let's say the limit of f of x is 0 and the limit of g of x is also 0. So that means f of x over g of x, that is 0 over 0. So what is the value of 0 over 0? We can think that 0 over 0 can be 0, can be infinity, can be a finite number. That means we are not sure that which one is the result. So that's why 0 over 0 is called an indeterminate form. That's why the word indeterminate means something which is not exactly known. So why 0 over 0 is an indeterminate form? We can answer in three different ways. Suppose we have 0 over 1. We know 0 over 1 will be 0. We have 0 over 2, the result will be 0. We may have 0 over 3, the result will be 0. So in similar fashion, if we think about 0 over 0, that can be also 0, because 0 over 1, 0, 0 over 2, 0, 0 over 3, 0. So we can write 0 over 0 as 0. This is the first case. We can also think like another way, that is, suppose we have 1 over 0. So it may be plus infinity. 2 over 0, it is also plus infinity. 3 over 0, it is also plus infinity. So if we follow this pattern, then 0 over 0 can be infinity. So this is the second case. 1 over 0, infinity. 2 over 0, infinity. 3 over 0, infinity. So why not 0 over 0 is infinity? We can also think about another way. Suppose we have 1 over 1, so the result will be 1. 2 over 2, the result will be 1. 3 over 3, the result will be 1. So in similar way, we can write 0 over 0 as 1. This is also possible. So that means 0 over 0 can be 0, can be infinity, can be a finite number. So that's why for a single case, we have three different scenarios. So that means we can't exactly say what is the value of 0 over 0. So that's why 0 over 0 is an indeterminate form. Similarly, if we have the same limit and the limit of f of x approaches to infinity, the limit of g of x approaches to infinity when x approaches a. So we can see that there is another form here, infinity over infinity. So we can't say what is the exact value of infinity over infinity. So there is a struggle between this numerator and denominator. If the numerator wins, the result may be infinity. If the denominator wins, the result will be 0. Or sometimes there will be a compromise between numerator and denominator, then the result will be a finite number. Just like 0 over 0, we can also think about infinity over infinity. So, for example, let's say we have 1 over infinity, we know this is 0. We have 2 over infinity, that will be 0. 3 over infinity, that will be 0. So that means infinity over infinity can be 0. We can also think like another way. Suppose we have infinity over 1, that is infinity. Infinity over 2, that will be infinity. Infinity over 3, that will be obviously infinity. So if we follow this pattern, then infinity over infinity will be infinity. Similarly, we can think like another way. Suppose we have 1 over 1, that is 1. 2 over 2, that will be 1. 3 over 3, that is also 1. That means if we have same number in numerator and denominator, the result will be 1. So we have infinity over infinity, that will be also 1 if we follow this pattern. So that means just like 0 over 0, infinity over infinity can be 0, can be infinity, can be a finite number. So we can easily say that infinity over infinity is another indeterminate form. So whenever we are going to evaluate the limit of f of x over g of x as x approaches a, so at that time, if we have 0 over 0 or infinity over infinity, then we can't exactly say what is the result of the limit. Limit may exist or may not exist. So 0 over 0 and infinity over infinity are called indeterminate forms. So besides 0 over 0 and infinity over infinity, we have some other indeterminate forms. So let's write all the indeterminate forms. Indeterminate forms can be classified into 5 types. The first type that we have is 0 over 0. The second type is infinity over infinity. The third type is 0 times infinity. The fourth type is infinity, negative infinity. And the fifth type is 0 power 0, infinity power 0, 1 to the infinity. So all these are called indeterminate forms. This is indeterminate form of type 0 over 0. This is indeterminate form of type infinity over infinity. This is indeterminate form of type 0 times infinity. This is a type of infinity, negative infinity. This is another indeterminate form of type 0 to the 0, infinity to the 0, 1 to the infinity. So for convenient, we can say that this is type 1, this is type 2, let's say this is type 3. We can say infinity, negative infinity, this is type 4, and the last one we can say this is type 5. So here I need to mention that we have infinity over infinity. We can also think about some subcategories here. It may be negative infinity over positive infinity, or positive infinity over negative infinity, or negative infinity over negative infinity. That means all these are infinity over infinity type. Similarly, for the third type, we may have infinity times 0, negative infinity times 0, 0 times negative infinity, So all these are called 0 times infinity type. So we know why 0 over 0 and infinity over infinity are indeterminate forms, because these two can give us several results. So we are getting crazy behaviors. In similar way, we can think why 0 times infinity, infinity negative infinity, 0 to the 0, infinity to the 0, 1 to the infinity are indeterminate forms. So let's say we have 0 times infinity. So there is always a contest between 0 and infinity. The result will be 0. The result may be infinity. Or the result may be a finite number. Similarly, there is a contest between infinity, negative infinity. If this wins, then the result will be plus infinity. If this wins, the result may be negative infinity, or this may results in a finite number. So this is how we can say that 0 times infinity and infinity minus infinity are indeterminate forms. Similarly, we can think about 0 to the 0, infinity to the 0, 1 to the infinity. These are also indeterminate forms. So for simplicity, we have mentioned that 0 over 0 is of type 1, infinity over infinity is of type 2, 0 times infinity is of type 3, infinity negative infinity is of type 4, 0 to the 0, infinity to the 0, 1 to the infinity are of type 5. So our target is to evaluate the limit of f of x over g of x. So suppose we want to evaluate the limit of f of x over g of x when x approaches to a. So if initially we have 0 over 0 or infinity over infinity, so we can apply L'Hopital's rule to evaluate the limit. So now we have to know what is L'Hopital's rule. Then we will discuss the procedure how to solve this limit. So what is L'Hopital's rule? We can see that L'Hopital's rule can also be written in this way. In this spelling, we have S, but this will be silent. So we can say L'Hopital's. We can see that f and g, that is f of x and g of x, are differentiable functions. That means we can differentiate f of x and g of x. So the differentiation of f of x is f prime x. The differentiation of g of x is g prime x. So if the limit of f of x goes to 0 and the limit of g of x goes to 0 as x approaches a, that means we have 0 over 0. We can also think in another way. If the limit of f of x goes to infinity and the limit of g of x also goes to infinity, that means we have infinity over infinity. So we have indeterminate form of type 0 over 0 and type infinity over infinity, that is type 1 and type 2. So if we have indeterminate forms of type 0 over 0 and infinity over infinity, then only we can apply L'Hopital's rule. So L'Hopital's rule says that the limit of this function will be equal to the limit of f prime x over g prime x. Now we can see that this right side limit may exist or maybe plus infinity or minus infinity. That means there are three scenarios here. the limit of f of x over g of x will be equal to the limit of f prime x over g prime x as x approaches a. So this limit may exist or it may be plus infinity or minus infinity. So whatever result we will have for these derivatives, that result is for the main part. So this is the L'Hopital's rule. So L'Hopital's rule is only applicable whenever we have a 0 over 0 or infinity over infinity. Otherwise, we can't apply L'Hopital's rule. So let's have a look on type 1 and type 2 again. That is type 1 and type 2. So type 1 says that we have 0 over 0. Type 2 says that we have infinity over infinity. So we are going to evaluate the limit of f of x over g of x as x approaches a. So here I need to mention that instead of x approaches a, we may have x approaches a plus, that is a from the right. We may also have x approaches a minus, that is a from the left. We may have x approaches plus infinity, or we may have x approaches minus infinity. So sometimes we may have these cases also. That is, instead of x tends to a, we may have x tends to a plus, x tends to a minus, x tends to plus infinity, or x tends to minus infinity. You will understand if we solve some examples. But remember, these plus or minus signs are just the direction. Plus means we are coming to A from the right. Minus means we are coming to A from the left. So our target is to evaluate this limit. So we are sure that f of x over g of x is giving us either 0 over 0 or infinity over infinity. That means we have type 1 or type 2. So if we have type 1 or type 2, then only we can apply L'Hopital's rule. So we have seen from the theorem that the limit of f of x over g of x will be the limit of f prime of x over g prime of x as x approaches a. That means we have to find first derivatives of f of x and g of x. So let's have a look on the procedure how we can solve this limit. So at first, in step 1, we have to check whether this limit is of 0 over 0, infinity over infinity, or not. If it is 0 over 0 or infinity over infinity, then only we can apply L'Hopital's rule. From the theorem of L'Hopital's rule, we can see that we have to find the derivatives of the functions. That means we have to differentiate f of x and g of x separately at the same time. Then we will have a prime of x and g prime of x. This is step 2. So in step 3, we have to find the limit of f prime of x over g prime of x. That means limit of f prime of x over g prime of x. So this limit may exist, maybe plus infinity, maybe minus infinity. So there are three scenarios here. So we can say that if we have to evaluate the limit of f of x over g of x as x approaches a, then we have to first check whether it is of 0 over 0, infinity over infinity or not. If it is of 0 over 0, we can apply L'Hopital's rule. If it is of infinity over infinity, we can apply L'Hopital's rule. So in step 1, we have to check whether it is of 0 over 0 or infinity over infinity or not. Then in step 2, we have to find the derivatives of f of x and derivatives of g of x. That is, we are differentiating f of x and g of x separately at the same time. Step 2 is this one. That means we have limit x tends to a. Differentiation of f of x is the same thing, f prime of x. Differentiation of g of x is g prime of x. So whatever result we will have for this one, that result will be for the left part. That is limit of f of x over g of x as x approaches a. So that means in step 3, we have to find the limit of this part. So here the result may exist, or it may be plus infinity, it may be minus infinity. That means we will have three scenarios. But sometimes in step 3, we can do some simplifications. Simplifications means suppose we have x cubed over x squared. So we can simplify. That is, if we cancel x cubed over x squared, we will get just x. So I am trying to say about this one. Sometimes in step 3, we may again get 0 over 0 or infinity over infinity. That means we have to differentiate again. That means step 2 will be repeated. So at first, we have to check whether we have 0 over 0 or infinity over infinity or not. If we have this, then we have to differentiate f of x and g of x separately. This is called L'Hopital's rule. And then we can find the limit of f prime of x over g prime of x. But despite doing the differentiation of f of x and g of x, this f prime over g prime may sometimes give us again 0 over 0, infinity over infinity. So in that case, again, we have to differentiate f prime and g prime. Then we will get f double prime over g double prime. Then we can check again. If we get 0 over 0 or infinity over infinity, then we have to differentiate again. So this process will be repeated. The process will be terminated if limit exists, or if we have only plus infinity or minus infinity. So limit exists means we have a finite number. So let's have a look on one example. Then we will understand how L'Hopital's rule can be applied in evaluating limits. So let's say we are going to evaluate the limit of x squared negative 4 over x negative 2 as x approaches to 2. We can solve this problem by using algebraic manipulation. First, have a look how I am solving this one. So limit of x squared negative 4 over x negative 2, it can be rearranged like x squared negative 2 squared. So 2 squared is 4. So we can write this. And in denominator, we have x negative 2. So limit x tends to 2. We can think this one as a squared negative b squared. That means we have a plus b times a minus b. We have two factors, x plus 2 times x minus 2 over x negative 2. So now we can simplify. So we have finally x plus 2. This is the simplified part. So now we can input the value of x where we have x. So this is the location of x. Let's input 2, 2 plus 2. That means we have 4. So the limit of this function when x approaches to 2 is equal to 4. So this is what we know as algebraic manipulation method. But the same problem can be solved by L'Hopital's rule. So let's say this is method 1, and now we are going to solve the same problem by using another method that is known as L'Hopital's rule. Before solving this problem, first of all, have a look on the steps of L'Hopital's rule. So in step 1, we have to check whether it is of 0 over 0 or infinity over infinity type or not. Then we can differentiate f of x and g of x if we have these types, otherwise not. And finally, we can evaluate the limit of f prime over g prime. So if we follow these 3 steps, then we can solve the problem. In step 1, we have to check whether it is of 0 over 0, infinity over infinity or not. So let's check initially. Here we have the location of x. Let's input 2 where we have x. So that means we can do a rough x squared negative 4, that is 2 squared negative 4, and in denominator we have x negative 2, that is 2 negative 2. So that is 4 negative 4 over 2 negative 2. We are getting 0 over 0. That means the limit that we have here, that is of 0 over 0 type. That means it is of type 1. We can say the limit is of indeterminate form of type 0 over 0. So since we have 0 over 0, now by using L'Hopital's rule, we can say we have to differentiate both f of x and g of x separately. So the top function is f of x, the bottom function is g of x. We are going to differentiate the top function x squared negative 4, and we have to differentiate the bottom function. So limit x tends to 2, differentiation of x squared is 2x, differentiation of negative 4 is 0, so no need to write 0 here. In denominator we have differentiation of x, that is 1, differentiation of negative 2 is 0. So we can see that we have f prime of x, g prime of x, that is step 2. Now we need to apply step 3. So before step 3, we have to check again that whether it is of 0 over 0 or not. So since in denominator we have 1, so there is no possibility of having 0 over 0 or infinity over infinity. That means we can terminate the process and find the result. So where we have x, let's plug 2. So 2 times 2 over 1, that is just 4. So it doesn't matter whether we apply method 1 or method 2. We are going to have the same result for this limit. But L'Hopital's rule is a systematic way that can help us in several problems. So sometimes it will be too difficult to solve the problems by using algebraic manipulation method, chains of variables. So in that case, we can apply L'Hopital's rule. But we have to be sure that we have 0 over 0 or infinity over infinity. So this is what L'Hopital's rule is. So let's say we are going to evaluate limit x approaches to 0 and the function is 1 negative cosine x over x squared. So first of all, we have to check whether it is 0 by 0 or infinity by infinity or not. So how can we check? Here we have x and x. Let's do a rough. Let's say we have 1 negative cosine 0 and 0 is squared. So that is, we are getting 1 negative cosine 0 is 1 and 0 is squared in denominator is 0. So we are getting 0 over 0. So that means the form we have here, that is of 0 over 0 type. So since it is 0 over 0 type, we can apply L'Hopital rule. So using L'Hopital rule, we can write limit x tends to 0, differentiation of 1 negative cosine x, differentiation of x squared. Since it is 0 over 0 type, that's why we are differentiating both functions separately. We are differentiating f of x, we are differentiating g of x. So limit x approaches to 0, differentiation of 1 is 0, differentiation of cosine x is negative sine x. In denominator, we have differentiation of x squared. So the result will be 2x. So let's simplify. We have limit x tends to 0, sine x over 2x. So again, we have to check. Let's do a rough here. So this is the location for x and it is the location for x in denominator. Again, we are going to check whether it is 0 by 0 or infinity by infinity or not. So sine x, that is sine 0, 2x, that is 2 times 0. So we are getting sine 0 means 0, 2 times 0, 0. So again, we have found 0 by 0 type. So that means we have to differentiate again. So we are differentiating sine x separately and we have to differentiate 2x separately. So limit x approaches to 0, differentiation of sine x is cosine x, differentiation of 2x is 2. So now you can obviously see that in denominator we have 2. So there is no possibility of having 0 over 0 or infinity over infinity. So that means this is our final result. That means just we can plug the value of x, that is x equals 0. So cosine 0 over 2. So we know that cosine 0 is 1 and in denominator we have 2. So this is the limiting value of this function when x approaches to 0. So in this example, you have seen that initially we have checked whether it is of 0 by 0 or infinity by infinity type or not. So we are sure that this is 0 over 0 type. So that means we can apply L'Hopital rule. So L'Hopital's rule says that whenever we have 0 over 0 or infinity over infinity, in that case we can differentiate both f of x and g of x separately. And then we have found this. Again, we have to check whether it is of 0 over 0, infinity over infinity or not. So if it is again 0 over 0 or infinity over infinity, we have to differentiate again. That's why we have differentiated sine x and 2x separately. And finally, we are getting the result. So we can say that the limiting value of this function when x approaches to 0 is equal to 1 over 2. This is by using L'Hopital's rule. So let's solve. Limit of e to the x negative 1 over sine x when x approaches to 0. So first of all, we have to check whether it is 0 over 0 or infinity over infinity or not. So let's check. Here we have x part and here we have also x. These are the locations where we are going to plug the value of x equals 0. So that is e to the 0 negative 1 over sine 0. So e to the 0, this is 1, negative 1. Sine 0, that is 0. So we are getting 0 over 0. So that means whatever function we have e to the x negative 1 over sine x, its limiting value when x approaches to 0 is giving us the type 0 over 0. So this is of 0 over 0 type. So that means we can apply L'Hopital rule. So using L'Hopital rule, we have to differentiate the upper function and we have to differentiate this function sine x also. So limit x approaches to 0. Differentiation of e to the x is e to the x. Differentiation of negative 1, so it is 0. Differentiation of sine x is cosine x. So now we have to check again whether it is of 0 over 0 type or infinity over infinity type or not. So let's do a rough. Here we have x and x. So e to the 0 cosine 0. That means e to the 0 is 1, cosine 0 is 1. It is not 0 over 0. We are getting a finite value. So that means this is our final result. So we can say that limit x tends to 0, e to the x cosine x, e to the 0 cosine 0. That is, we have 1 over 1. So the result is 1. So that means the limiting value of this function when x approaches to 0 is 1. So I have mentioned that 0 over 0 is the first type, infinity over infinity, that is the second type, which are known as indeterminate forms. So we have learned how to deal with 0 over 0. Let's solve one example, which is of infinity over infinity. Let's say we have to calculate the limiting value of e to the x over x squared when x approaches to plus infinity. So we have f of x over g of x. F of x is e to the x, g of x is x squared. So first of all, let's check whether it is of infinity over infinity or not. So at first we need to find the locations of x. So e to the x, that means e to the infinity. We are plugging this part over infinity squared. So e to the infinity will give us infinity. Infinity squared, that is again infinity. So that means it is of infinity over infinity type. So since we have infinity over infinity, we can apply Lopital rule. So using Lopital rule, we can solve this problem. That means we have to find the derivative of e to the x. We have to also find the derivative of x squared. So limit x tends to infinity, ddx of e to the x over ddx of x squared. Whatever result we will get for this, the same result holds for the main problem. So limit x tends to infinity, ddx of e to the x is e to the x, ddx of x squared is 2x. So first we have infinity over infinity type. That's why we have applied L'Hopital's rule. L'Hopital rule says that differentiate both f of x and g of x separately. And finally, we have found the simplified form. Again, we have to check whether it is of infinity over infinity or not. So we have the location x and x. So let's plug infinity, e to the infinity over 2 times infinity. That means we are getting infinity over infinity. E to the infinity will give us infinity. 2 times infinity is infinity. So that means the simplified form that we have found here, it is still infinity over infinity type. So limit x tends to infinity, e to the x over 2x. So we have understood that this is again of infinity over infinity type. So that's why we have to differentiate again. So limit x tends to infinity, ddx of e to the x, ddx of 2x. So we are getting limit x tends to infinity. Differentiation of e to the x in terms of x is e to the x. Differentiation of 2x is 2. So now we can understand that there is no possibility of having infinity over infinity again, because in denominator we have 2. So that means we can terminate the process here. So that's why this is the time to plug the value of x. So e to the infinity over 2. That means we are getting infinity over 2. So infinity over 2 will be infinity. That means we have plus infinity. So the limiting value of e to the x over x squared when x approaches to infinity is plus infinity. So say we have to evaluate the limiting value of tangent of x negative x over x cubed when x approaches to 0. So first of all, we have to check what is the type. So here we have x, x, and x. We are locating these portions so that we can plug this value. So let's do a rough. So tan x, that is tangent of 0, negative x, negative 0, x cubed, that is 0 cubed. So we are getting Tangent of 0 is 0. 0 negative 0 is obviously 0. 0 cubed, that is 0. So that means the problem is of 0 over 0 type. So we can apply L'Hopital's rule. So that means we have to differentiate tangent of x negative x, and we have to differentiate x cubed. So we are using L'Hopital's rule. So limit x tends to 0. Now we know that differentiation of tangent of x is secant squared x. Differentiation of x is 1, and here we have a negative sign. In denominator, differentiation of x cubed, so it is 3x squared. Now again, we have to check what is the type of this simplified portion. So this is the location where we can input the value of x. Here we have x. So secant squared 0 negative 1 over 3 times 0 squared. So secant squared 0. That means we can think about 1 over cosine squared 0, negative 1. And in denominator, we have 3 times 0, that is 0. So we can write like this. 1 over cosine squared 0. So you know that cosine 0 is 1. So 1 over 1, negative 1 over 0. So that means in upper part, you are getting 1 negative 1, that is 0. So it is of 0 over 0 type. So we have to do this graph so that we can understand the type of the simplified function. So we have limit x tends to 0, secant squared x negative 1 over 3x squared. So since this is again of 0 over 0 type, so we have to differentiate the numerator and we have to differentiate the denominator separately. So let's do limit x tends to 0, differentiation of secant squared x negative 1, and in denominator differentiation of 3x squared. So limit x tends to 0. In denominator we have differentiation of 3x squared, so 3 can be pulled out. We have differentiation of x squared. So this is what we have in denominator. In numerator we can write like differentiation of secant squared x negative differentiation of 1. So this time I am explaining whatever process we have to do here. So limit x tends to 0, 3, differentiation of x squared is 2x, differentiation of 1 is 0. But what is the derivative of secant squared x? So this is by chain rule. secant squared x can be written in this way, that is secant x power 2. So now we can think about differentiation of x squared, that is 2x, differentiation of u squared is 2u if it is u. So we have here differentiation of secant x squared. What will be the result? We can apply chain rule. So we can consider this one as x. So let's say instead of secant x, we have only x. So differentiation of x squared will be 2x. That means 2 secant x. And since we have considered secant x as x, we have to differentiate secant x again. This is what we know as chain rule. So limit x tends to 0. In denominator we have 3 times 2x, that is 6x. And differentiation of secant squared x will be 2 secant x times differentiation of secant x again. This is by using chain rule. Now limit x tends to 0. In denominator we have 6x. In numerator we have 2 secant x. Now it is easy. Differentiation of secant x, it is secant x tan x. We can simplify, that is it is now 2 secant squared x times tan x over 6x. So here we can also simplify this, that is in numerator we have 2, in denominator we have 6, so it will be 1 over 3. So instead of 2 and 6, we are writing 1 over 3. That means we just have this function now, secant squared x tan x over 3x. So now this is the time to check again what is the value of this upper function and this lower function. If it is 0 over 0 again, then we have to differentiate again. Let's do a rough again. So here we have x, x, and x. So these are the locations of x. If we input 0, that means secant squared 0, tan 0 over 3 times 0. So we are getting 0, secant squared 0 is 1, tan 0 is 0. So 0 over 0 type. So that means again we have to apply L'Hopital's rule. So this is of 0 over 0 type. So that means we have to differentiate again. So limit x tends to 0, differentiation of secant squared x tan x, and differentiation of x. We are applying again L'Hopital's rule because we have 0 over 0 type. So limit x tends to 0. Here we have 3 also. So 3 times differentiation of x is 1. In numerator, this time we have differentiation of u times v. So we know that if we have differentiation of u times v, then we can write as u ddx of v plus v ddx of u. So using this concept, we can find the derivative. So let's say secant squared x as u and tangent of x as v. So we have secant squared x ddx of tan x plus tan x ddx of secant squared x. So limit x tends to 0, we have 3 here, secant squared x, differentiation of tan x. So differentiation of tangent of x, it is nothing but secant squared x, plus we have tan x, and again we have differentiation of secant squared x. So just now we have done the same thing. What is the differentiation of secant squared x? By using chain rule, we have found it is 2 secant x tangent of x. So same thing is coming. I am writing directly here. That is 2 secant squared x times tan x. Limit x tends to 0. Let's do the simplification here. So we have secant x to the 4, or we can write like secant 4x. We have 2 secant squared x tan squared x over 3. So this time you can see that in denominator we have 3. So there is no possibility of having infinity over infinity or 0 over 0 here. So that means we can stop here. We can input the value of x equals 0, where we have x. This is the time to write directly. So here x will be 0, 2 secant squared 0, tan squared 0 over 3. So there is no option for differentiation again, because we don't have 0 over 0 type or infinity over infinity type here. So that's why we are plugging this value. So we have 3 in denominator. So secant power 4 of 0 will be 1 plus 2 secant squared 0, it is 1, tangent squared of 0, that is 0. So we have 1 plus 2 times 1 times 0, that is, it is 0 by 3. So actually we have 1 over 3. Finally, we are able to solve the problem. That means the limiting value of this function when x approaches to 0 is 1 over 3. So this is our final answer. So we have learned how to deal with 0 over 0 or infinity over infinity. Now let's focus on this type if we have 0 times infinity or infinity times 0. Same thing. This is another indeterminate form. So if we have limit f of x times g of x when x approaches to a. So at first we have to understand the general concept, then we will move to the problem solving part. So this is of type 3. that is 0 times infinity or infinity times 0. So I have mentioned that x tends to a can be also x tends to a plus, a minus, plus infinity. It can be negative infinity also. So it depends. Initially, we have to check what is the type. So this time, we don't have f of x over g of x form. We have f of x times g of x form. So that means initially if we plug the value of x in this function, it may give us 0. And the second function may be infinity. So we have 0 times infinity form. Also, the first function f of x may give us infinity, and the second function g of x may be 0. So infinity times 0 or 0 times infinity, this is the third type, which is known as another indeterminate form. So if we have 0 times infinity, that is the third type, we can't apply L'Hopital's rule directly. So in that case, anyhow, we have to convert f of x times g of x into f of x over g of x form. So we have to write this product form as a quotient form or as a ratio form, so that we have f of x over g of x. That means we have 0 over 0 or infinity over infinity. So that means in step 1, if we have 0 times infinity or infinity times 0, that means we have the product f of x times g of x. We have the multiplication part of f of x and g of x. So first step will be we have to convert this product form to the ratio form, that is f of x over g of x form, so that we may have 0 over 0 or infinity over infinity type. Then in step 2, we can apply L'Hopital's rule, that is whatever we know for 0 over 0 and infinity over infinity. So all process will come here. But first step is to convert this product form to the ratio form. So you will understand if I show you one example. So let's say we are going to evaluate the limit of, let's say, x times natural log of x when x approaches to 0 plus. Limit x tends to 0 plus x times natural log of x. So we know that this plus is just a direction. We actually have x tends to 0. This is the thing. That means first we have to locate x. So here we have x and x. So let's input 0. So 0 times natural log of 0. So 0 times natural log of 0, it is actually negative infinity. I can show here that is natural log of x. If we plot this function, we can see if we come from the right, then the function is coming here. That means it is going to negative infinity. It is going downward to negative infinity. So it's not positive infinity, it's negative infinity. So natural log of 0 will be negative infinity. So we have 0 times negative infinity. It is also the same thing as 0 times plus infinity, infinity times 0. So we may have 0 times negative infinity also. But the main theme is we have the product of 0 and plus infinity or minus infinity. So it is of 0 times negative infinity form. That means it is of type 3. So what we have to do, I have mentioned here that anyhow we have to convert this product form to the ratio form. So can we write this one as natural log of x over 1 over x? We can write, because if we do the simplification we will get the same thing. So this is the idea behind 0 times infinity, infinity times 0, or 0 times negative infinity times 0. We have to rewrite the functions f of x times g of x as a ratio form. We can think about, if we have f times g, we can write like f over 1 over g, or f times g can be written as g over 1 over f. So this is how we can convert the product to the ratio form. So I have done the same thing here. So here I have x, I have written this one as 1 over 1 over x. So if I simplify again, natural log of x divided by 1 over x, so natural log of x times x by 1. So that means we are getting same thing. So we can do this simplification. We have rewritten the function as a ratio form. Now this is the time to check again what is the type now. So if we input 0 here and 0 here, let's see what happens. Natural log of 0, 1 over 0. So natural log of 0, that is negative infinity, 1 over 0, that is positive infinity. So we are getting infinity over infinity type. So that means it is of negative infinity over infinity type. So we can differentiate. Limit x tends to 0 plus. Now we can apply L'Hopital's rule because we have found infinity over infinity form. Yeah, we have negative infinity here, and in denominator we have positive infinity, but that is not the thing. We have infinity over infinity. That is the main concept. So if we have infinity over infinity, in that case, we can apply L'Hopital rule. That is, we can differentiate both upper function and lower function separately at the same time. So no matter we have whether plus infinity or minus infinity, the main concept is we have infinity in numerator, we have infinity in denominator. So ddx of natural log of x, ddx of 1 over x. Now natural log of x, its differentiation will be 1 over x, and differentiation of 1 over x. 1 over x can be written as x to the negative 1. So we know that ddx of x to the n is nx power n negative 1. So differentiation of x to the negative 1 will be negative 1 x negative 1 negative 1. So finally we have negative 1 x to the negative 2. So that is negative 1 over x squared. So this is the result what we can write in denominator. And we have x tends to 0 plus. So here we have 1 over x and in denominator we have negative 1 over x squared. We can simplify before checking. So 1 over x times negative x squared over 1. So we can simplify this. Now we can see this will be x. So limit x tends to 0 plus. In numerator we have negative x, and in denominator we have 1. So we can understand that there is no possibility of having 0 over 0 or infinity over infinity again here, because we have 1 in denominator. So that means we can terminate the process. We don't need to differentiate again. We don't need to apply L'Hopital's rule here. So limit x tends to 0 plus negative x. So now the time is to input this value. So remember that 0 plus is just the direction. Actually we have 0. So we can write limit x tends to 0 negative x. We can skip this plus sign. Now where we have x, let's plug 0. So finally we have found 0. So the limit of this function x natural log of x when x approaches to 0 plus is 0. So this is how we can solve if we have type 3, that is 0 times infinity, infinity times 0, 0 times negative infinity times 0. That means multiplication of 0 and infinity. So let's solve another similar problem. Let's consider we have a function x e to the negative x with limit x tends to plus infinity. So we have the function x times e to the negative x. We have to evaluate this limit. First, we have to understand the type. So this is our location of x, and here we have x. That means infinity times e to the negative infinity. So we know e to the infinity is infinity, e to the negative infinity is 0. So that means infinity times 0. So the function that we have with this limiting concept has the type infinity times 0. So we have type 3. That means first we have to convert this product form to the ratio form so that we may have 0 over 0 or infinity over infinity. And in next steps, we have to apply L'Hopital's rule. So we have found infinity times 0 type. That means anyhow we have to rewrite this product form to the ratio form. So limit x tends to infinity. We can write x in numerator part. In denominator, we can write e to the x. So if we check again, we will see that 1 over e to the x is e to the negative x. So that means whatever I have written here, same thing is here. Just I have found the reciprocal of e to the negative x. So e to the negative x can be written as 1 over e to the x. So my target is to write this product form to the ratio form. And finally, I am successful to write this product form to the ratio form. So now, automatically, we may have 0 by 0 or infinity by infinity form here. So since we have plus infinity here, let's look at the positions for x. So again, we are checking in numerator we have infinity, in denominator we have e to the infinity. So in numerator infinity and e to the infinity, we know it is infinity. So we have infinity over infinity type. So that means we can apply L'Hopital's rule. So L'Hopital's rule says that we have to differentiate f of x and g of x separately at the same time. So limit x tends to infinity, differentiation of x, differentiation of e to the x. Limit x tends to plus infinity, differentiation of x is 1. Differentiation of e to the x is the same, e to the x. So now we can easily understand that there is no possibility of having infinity over infinity or 0 over 0 here, because in numerator we have a real number 1. So we can terminate the process here and we can find the limiting value. So here we have x. Let's plug 1 over e to the infinity. So that means we are getting 1 over infinity, because e to the infinity is infinity. So we know that 1 over infinity is 0. So finally, this is our result. That means limit of this function when x approaches to plus infinity becomes 0. This is what we know as type 3. And let's see how to solve if we have type 4 problems. That means if we have infinity, negative infinity. So whenever we have infinity, negative infinity form, again the process is same. Anyhow, we have to convert to 0 over 0 or infinity over infinity. Now type 4. So first have a look on the general concept. We have subtraction, f of x negative g of x. So if we target for finding the limiting value of this function, then we may have infinity, negative infinity. That is, the first function initially may give us infinity, the second function may give us infinity. So this is of type 4. So infinity, negative infinity is another indeterminate form. So if we have this case, we have to convert infinity, negative infinity to either 0 over 0 or infinity over infinity form. So this is step 1. So once we have 0 over 0 or infinity over infinity, then it is easy to apply L'Hopital's rule. So in next steps, we will apply L'Hopital's rule. But first, we have to confirm that we have 0 over 0 or infinity over infinity. So how can we convert infinity, negative infinity to 0 over 0 or infinity over infinity? We have to understand the concept. So we can do this one by using LCM. That means we can combine the two functions so that we have finally f of x over g of x form. In step 1, we have to make a common denominator, or we can rationalize, we can factor out some part so that it may become f of x over g of x form. And finally, if we can do so, then we will have 0 over 0 or infinity over infinity type. Then we can apply L'Hopital's rule. So for example, let's solve one problem. Let's say we have limit x tends to 1 plus 1 over natural log of x negative 1 over x negative 1. So limit x tends to 1 plus 1 over natural log of x negative 1 over x negative 1. So again, I have given here a plus sign, but that is just a direction. It is denoting that we are coming to 1 from the right. So we can skip that plus sign later. So actually we have 1 here. So first we have to check what type is this one. So we have the position for x. This is x. Let's plug 1. So we are doing a rough here. So 1 over natural log of 1 negative 1 over 1 negative 1. That means where we have x, I have just plugged the value of x as 1. So 1 over natural log of 1 is 0. Negative 1 over 0. So 1 over 0 is infinity. Negative 1 over 0 is infinity. So that means the problem that we have here, it is of infinity, negative infinity type. Here we have learned that if we have infinity, negative infinity, then we can combine that two functions by using the concept of LCM. So let's do the LCM here. Our main problem is limit x tends to 1, 1 over natural log of x, negative 1 over x negative 1. So limit x tends to 1. We are going to do the LCM. Here it will be natural log of x times x negative 1. Here it will be x negative 1, then we have negative, and it will be natural log of x. So we have 1 plus. Now we have found a ratio form, f of x over g of x. So what concept we have done here? We have applied the concept of LCM. We have combined these two functions so that we may have a single function. And it is now like f of x over g of x form. So this is the time to check whether it is 0 over 0 or infinity over infinity or not. Definitely, if your LCM is correct, we must have 0 over 0 or infinity over infinity type. So let's check. This is the position x, 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 x. So let's do a rough. We are going to plug 1, x negative 1, that is 1 negative 1. Negative natural log of 1 over natural log of 1, 1 negative 1. So we are getting 1 negative 1 is 0, negative natural log of 1 is 0, natural log of 1 is 0, 1 negative 1 is 0. So 0 negative 0 is 0, 0 times 0 is 0. So the form that we have here, it is of 0 over 0 type. So that means step 1 is done. We can apply L'Hopital's rule. So let me write again. So limit x tends to 1 plus x negative 1 negative natural log of x. So natural log of x times x negative 1. So it is of 0 by 0 form. So that means we can apply L'Hopital's rule. That means we can differentiate the upper function x negative 1 negative natural log of x, we can differentiate natural log of x times x negative 1. Now we have to apply the concept of derivative. Limit x tends to 1. So differentiation of x is 1. Negative differentiation of 1 is 0. Negative differentiation of natural log of x, we know it is 1 over x. So the calculation for the numerator part is done. Let's do the calculation for the denominator. So in denominator, we have ddx of u times v. So we know that if we have ddx of u times v, we can write u ddx of v plus v ddx of u. We can consider natural log of x as u and x negative 1 as v. So u ddx of v plus v ddx of u. So we have limit x tends to 1, 1 negative 1 over x. In denominator, natural log of x, differentiation of x will be 1, differentiation of 1 is 0. So I am just writing 1 here, plus x negative 1. Differentiation of natural log of x, it is nothing but 1 over x. So first, let's do the simplification again, and then we'll focus on the next step. So limit x tends to 1, 1 negative 1 over x, natural log of x times 1 is natural log of x, plus we have x negative 1 over x. So in this part, what we can do, we can simplify again. That is limit x tends to 1, x negative 1 over x, x. So x times natural log of x plus x negative 1. So we can simplify if we want. Now we have limit x tends to 1, x negative 1 over x times x over x natural log of x plus x negative 1. So obviously this x and this x can be cancelled. So we have limit x tends to 1, x negative 1, x times natural log of x plus x negative 1. So this is our simplified part. Again, we have to check what is the type of this simplified form. So here we have x, 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 x. Let's check again. Let's do a rough. So 1, 1 negative 1. 1 times natural log of 1 plus 1 negative 1. So we are getting 1 negative 1 as 0. Natural log of 1 is 0, 0 times 1 is 0, plus 1 negative 1, 0. So we have 0 over 0 again. So that means we can apply L'Hopital's rule again. Since we have 0 over 0 type here, so it allows us to take the help of L'Hopital's rule. So that means we have to differentiate again. So limit x tends to 1, differentiation of x negative 1, differentiation of x natural log of x plus x negative 1. So what is the reason behind doing this differentiation? This is because it is of 0 over 0 type. So that's why we have differentiated the upper function and the bottom function. So now we have limit x tends to 1. Differentiation of x is 1. Differentiation of 1 is 0, so no need to write that. And here, since it is like u times v, so we can do this calculation later. That means we can separate natural log of x times x and its differentiation plus ddx of x negative 1. I have separated this part and this part. Using summation rule of differentiation, we can separate this. So limit x tends to 1, 1 over, there is something here, plus differentiation of x is 1. Differentiation of negative 1 is 0. So we have just 1 here. And now we can see that we have u times v. So derivative of u times v says that u ddx of v plus v ddx of u. So x ddx of natural log of x plus natural log of x ddx of x. So we have to simplify again. Limit x tends to 1, 1 over x. So differentiation of natural log of x is 1 over x plus natural log of x. Differentiation of x is 1 and we have plus 1. So now the time is to simplify. So we can see that x and x are here. So we can write like limit x tends to 1, 1 over 1 plus natural log of x plus 1. This time we are sure that there will be no 0 over 0 or infinity over infinity, because in upper part we have 1. So there is no possibility of having 0 in upper part. So there is no possibility of having 0 over 0 or infinity over infinity. So that means we can stop differentiation process. We don't need to take the help of L'Hopital's rule again here. So this is the time to directly input the value of x where we have x. So we have 1 over 1 plus natural log of x, that is natural log of 1 plus 1. So 1 over 1 plus 0 plus 1, because natural log of 1 is 0. So finally we have 1 over 2. So this is the result for this problem, which is of type 4, infinity, negative infinity. So let's talk about type 5. We may have 0 power 0, infinity power 0, 1 to the infinity. So what is the general form? Suppose we are going to evaluate the limit of f of x to the g of x. You can understand this time that we have a function with one exponent which is also a function. Just like you can consider x power sine x. It is f of x, and the exponent is also another function of x. So if we have this type of cases which are giving us 0 to the 0, that means if this function is giving us 0 and the exponent part is giving us 0, so this is an indeterminate form. This f of x may be infinity and the power g of x may be 0. So this is another indeterminate form. This function may be 1 and the power function may be infinity. So this is another indeterminate form. So this is what we know as type 5. So if we have these cases, so just to solve this problem, our target is to convert this f of x power g of x form to f of x over g of x. But how can we do this type of conversion? So this time we have to take the help of logarithm. That means we can take logarithm on both sides and then we can try to find the limiting value. So step 1, if we are confirmed that we have type 5, that is 0 power 0, infinity power 0, 1 to the infinity. So in that case, we have to consider, y for this function. Forget about the limit. So we are considering y as f of x power g of x. In next step, we have to take logarithm of both sides. That is logarithm of y, natural log of f of x power g of x. And we know a property of logarithm that if we have natural log of a power b, so we can write b times natural log of a. That means this power comes before. So we know this property. So what we can do, natural log of f of x power g of x, it can be written as g of x natural log of f of x. And in left side, we have natural log of y. So this time, we can see that we have product form, a function of x, another function of x. So if we have the product form, we may have 0 times infinity or infinity times 0. That means from type 5, we have now type 3. So if we have type 3, we know how we can convert this 0 times infinity or infinity times 0 to 0 by 0 or infinity by infinity. We know if we have fg, then we can write f over 1 over g. Or if we have fz, we can also write z over 1 over f. That means now we have type 3. So in next step, we have to convert this one as a ratio form so that we may have some parts in numerator and a function in denominator. Finally, the function that we have here, it will be of 0 over 0, infinity over infinity. Now we can take this limit. That means limit x tends to a f of x power g of x. So if we take limit x tends to 0, natural log of y, limit x tends to 0 of this function, we have f of x over g of x form. So finally, we can apply L'Hopital's rule and we will get the result. But the result that we will find here, that is not for the main function. That is not for y. That is not for f of x power g of x, that is for natural log of y. So from this part, we have to convert to y only, so that we have the result for this main function. So again, the steps are, at first we have to confirm whether it is of type 5 or not. If it is of type 5, then we have to consider y for that function and then take natural log on both sides. Automatically, you will have this property, natural log of a power b, that is b natural log of a. And finally, you will get a product form. Try to convert that product form to the ratio form and take this limit now. So you will get 0 over 0, infinity over infinity. That means we can apply L'Hopital's rule. But the result that we will find, that will be for natural log of y. But we aim to get y. Our target is to get only y. We can think about a problem. Let's say limit x tends to 0 plus 1 plus sine 4x cotangent of x. First, we have to check the type of this problem. So it is going with limit x tends to a f of x power g of x form. So that means we have to check whether it is of type 5 or not, whether we have 0 power 0, infinity power 0, 1 to the infinity or not. At first, look at x, where we are going to plug 0. So let's do the rough. 1 plus sine 4 times 0 cotangent of 0. So 1 plus sine 0 and cotangent of 0. So we know that cotangent of 0 is equal to 1 over tangent of 0. So 1 over tangent of 0 means 0. So 1 over 0 is infinity. So that means here it will be infinity. So 1 plus sine 0 is 0, infinity. So we have actually 1 plus 0, that means 1, 1 to the infinity. So out of this 3, we have 1, that is 1 to the infinity. That means it is of type 5. The problem that we have here, it is of type 5. So we have to consider this function as y. This is our first step. So let us consider y equals 1 plus sine of 4x to the cotangent of x. So this time, we don't need to think about the limit. We will take the limiting concept again. But for now, we are just considering the function as y. So now, we have to take the natural log of both sides. So natural log of y and natural log of 1 plus sine of 4x cotangent of x. So now we can see that on left side we have natural log of y, on right side natural log of a power b, that is b natural log of a. So the power can be pulled out before the logarithm. So cotangent of x times 1 plus sine 4x. So we can see that we have a product f of x times g of x. So that means if we check for the limiting value 0. That means cotangent of 0 will be infinity. Just now we have seen cotangent of 0 is infinity. And natural log of 1 plus sine 0, that is natural log of 1. Natural log of 1 is 0. So automatically we have type 3. So whatever I have described here, that is coming. That means now we have type 3. So if we have type 3, we can convert that type to the ratio form. So we have to convert this product to the ratio form anyhow. So natural log of y equals, we can do this, that natural log of 1 plus sine 4x, cotangent of x. I have just written cotangent of x can be written as 1 over tangent of x. So that means we have in denominator tangent of x. So our target is fulfilled, that we are able to convert this function to the ratio form. Now we can think about limit. So we are taking limit on both sides. Limit x tends to 0 plus natural log of y equals limit x tends to 0 plus natural log of 1 plus sine 4x tangent of x. So we don't need to think about the left side. Our target is to find the limiting value of the right side. If we want, we can also skip limit in left side. That means we can just think about, we just have natural log of y. We can think like that. So here, the value of x is 0. Let's check whether we have 0 over 0 or infinity over infinity or not. So the locations for x are here. So let's do a rough. Natural log of 1 plus sine 4 times 0, that means directly 0, tangent of 0. So natural log of 1, tangent of 0 means 0. So natural log of 1 is 0 over 0. So that means we have now found we have now found that it is of 0 over 0 type. So that means we can apply L'Hopital's rule. So let me write again. We have natural log of y in left side, limit x tends to 0 plus natural log of x 1 plus sine 4x tangent of x in denominator. So here we have limit x tends to 0 plus also. So we can apply L'Hopital's rule now, because the function that we have on right side, its limiting value goes with 0 by 0. It is like 0 over 0 type. So that's why we can apply L'Hopital's rule. That means we can differentiate both functions separately. So limit x tends to 0. No need to write plus again. So I am writing x tends to 0. So differentiation of natural log of 1 plus sine 4x and differentiation of tangent of x. So this time we have to apply the chain rule. for numerator part. So let's recall what is chain rule. We know that ddx of natural log of x, this is 1 over x. But here we have ddx of natural log of something. So that means we can consider this inner part as x. So differentiation of natural log of 1 plus sine 4x will be just like this. But see how I am doing this calculation. Consider we have x here. So natural log of x, its derivative will be 1 over x. That means 1 over 1 plus sine 4x. So the term that we have considered as x, that have to be again under differentiation. So we are going to do that technique here. So limit x tends to 0, differentiation of natural log of 1 plus sine x by using chain rule. We can write 1 over 1 plus sine 4x and differentiation of 1 plus sine 4x again. In denominator, differentiation of 10x, it is directly secant squared x. So limit x tends to 0, we have 1 over 1 plus sine 4x. Differentiation of 1 is 0. Differentiation of sine 4x. Again, we have to apply chain rule here because we know ddx of sine x, it is cosine x. But now we have sine 4x. So just consider instead of 4x, we have x. So ddx of sine 4x will be cosine 4x, and we have to differentiate 4x again. So cosine 4x, differentiation of 4x will be 4. So that is, here we are getting 4 cosine 4x. In denominator, we have secant squared x. So limit x tends to 0, 4 cosine 4x over 1 plus sine 4x over secant squared x. So we can simplify here if we want. That is limit x tends to 0, 4 cosine 4x 1 plus sine 4x times. We have 1 over secant squared x. So this time we can again input the value of x where we have x. Let's see whether we are getting 0 over 0, infinity over infinity or not. Let's do the rough. So 4 cosine 0 over 1 plus sine 0 times 1 over secant squared 0. So that means 4 cosine 0 is 1. 1 plus sine 0, that means 1 because sine 0 is 0 times 1 over secant squared 0. we can think about it is cosine squared 0. So cosine 0 is 1. So cosine squared 0 will be 1. That means we have 4 over 1 times 1. That is 4. So we don't have 0 by 0 type or infinity by infinity type. That means we can stop here. So limit x tends to 0, 4 cosine 4x, 1 plus sine 4x times cosine squared x. If we input the value of x, we have seen that it will be 4. So finally, we will get 4. So don't forget that in left side, we have natural log of y. And whenever I have described the general concept, I have mentioned that our target is to convert natural log of y to y only. Then we will get the main result. So here we have limit of natural log of y when x is approaching to 0. We can also skip this limiting concept. Our target is to find y only. So see how we can find. So we have natural log of y that is equal to 4. So we know that natural log of e is 1. So in next statement we can write natural log of y equals 4 times natural log of e. We can consider that with 4 we have 1. 4 times 1 is 4. So that's why we can take natural log of e. So this is the process of converting natural log of y to y only. So now you know that if we have b natural log of a, then we can write natural log of a power b. So in next step, we can write natural log of e power 4. Now we can recall another concept. If we have log a equals log b, then we can write a equals b. So we can see that log y equals log e to the 4. So log a equals log b. That means a equals b. So the function that we have previously, 1 plus sine 4x power cotangent of x, its limiting value is e to the 4. So this is our result. That is limit x tends to 0 plus the main function, whatever we have, 1 plus sine 4x power cotangent of x is equal to e to the 4. So we can write the main part again if we want. But this is our final result. So I hope you have understood how to deal with L'Hopital's rule. So that's all from me. Have a good time. Thank you.